Welcome to Module 9A from our series on artificial intelligence. This module addresses backpropagation. Specifically, it introduces backpropagation as a concept, demonstrates how to set up the necessary calculations, and provides a short visualization of the process. The next module defines the process in a more formal or mathematical manner. So let's begin by looking at an example. This will facilitate our discussion. We will consider an image recognition problem similar to that discussed in previous modules, for example, the handwriting recognition module, but we're going to use a simplified form. Why? Because a large part of this module requires us to do step-by-step handwritten calculations, and we want a simpler model to facilitate that process. So this neural network, this model only has two inputs that would be associated with two sensors for our spatial averaging. We only have two outputs, which correspond to two potential classifications or two categories. Like I said a second ago, we are going to manually, step-by-step, perform supervised machine learning for this shallow neural network. By applying backpropagation in conjunction with gradient descent, we'll demonstrate this process step-by-step. So here we see our shallow neural network. It has two inputs, it has two outputs, it has a single hidden layer that employs a rectified linear unit activation function. It has an output layer that employs a sigmoid activation function, and then we can see the notation for all the synapse weights. We are not going to discuss the training data in detail. Essentially, we have 10 training samples that were generated from handwritten symbols. We're going to apply spatial averaging as we did in many of the previous modules. And like I said a second ago, we're using two sensing regions, X1 and X2. And they are kind of tailored or gerrymandered to facilitate recognizing zeros and ones. We can see that for a 0, we have more ink in the red region and less in the blue, as compared to the 1, where we have more ink in the blue and less ink in the red. Before we discuss backpropagation, I did want to run through the characteristics of this specific machine learning example. So the learning paradigm, this is a supervised learning problem. The application, we are applying the machine learning to binary classification. The model that we are employing is a shallow neural network with a single hidden layer. And that model, that neural network, employs both rectified linear unit and sigmoid activation functions. The optimization method is stochastic gradient descent with backpropagation. Note that we are going to clarify finally the difference between batch and stochastic gradient descent in not the next module, but actually the second module or the next module. The loss function is mean squared error, one that we've seen in many previous modules. We've discussed that at length. The training data is labeled real world observations, right? The handwritten symbols. And the hyperparameters, we really only have one, and that's going to be a static learning rate. We're not going to be using an adaptive learning rate here, and we're not going to be discussing momentum or weight decay. Here we see our training data. We have 10 samples, like I said before. Each sample is composed of two input or input states, X1 and X2, as well as a labeled output. So what we see is that the first 5 samples are intended to be a 0, and the second 5 samples are intended to be a 1, and obviously we refer to that as the output. So now let's ask the key question associated with this module. What is backpropagation, and how does it relate to gradient descent? Backpropagation computes the gradients of loss or error with respect to each synapse weight parameter within a network, including those in the hidden as well as output layers, while gradient descent uses these tangents, uses these slopes to update relevant parameters such that loss or error is minimized. In short, backpropagation provides the gradient or the partial derivative of error with respect to W that the descent method uses or needs to perform updates and hopefully iteratively minimize the error/loss. Next, we provide an intro to backpropagation. Note there will be some repetition between the last slide and this one. So backpropagation computes the gradients of loss or error with respect to all the synapse weight parameters. It provides a partial derivative of the total error with respect to any synapse weight. For example, here we have the synapse weight between node or neurons K and M, and these gradients are required for optimization via descent. Now, in my mind, the term backpropagation implies that there is at least one hidden layer. It implies that we need to calculate gradients for the output as well as the hidden layer weights, and we'll see in a second that calculating this gradient for the hidden layer can be a little bit more difficult. Backpropagation employs the chain rule, the differentiation chain rule, to propagate errors back from the output to the input layer. Gradient descent is something that we've already discussed at length, so I'm just going to show the basic update expression. Gradient descent, if we're applying it to the synapse weights, right, we see here is the synapse weight between nodes K and M for the quote-unquote next iteration, IT plus 1, and that's generated from the previous iteration's corresponding synapse weight minus a learning rate coefficient times the appropriate partial derivative or appropriate component of the gradient. This right here is a minus because we're assuming that the goal is minimization. This would be a plus for maximization. So in short, backpropagation finds the gradients, and gradient descent uses them to minimize error or loss. So let's begin to discuss the backpropagation process in greater detail. What we'll see is that fortunately, it's relatively easy or relatively straightforward to differentiate the total error, or the two components of error, which we call E superscript 5 and E superscript 6. They correspond with x5 and x6. It's relatively easy to differentiate these error components with respect to the output layer synapse weights, as shown here W35, 45, 36, and 46. Why is that? In order to explain, let's take a look at our error function, our mean squared error function, for a given iteration and sample. One thing I want to note is that in my notation, if we have an expression where all the values are associated with a single iteration, and then in turn a single sample, if we're talking about stochastic gradient descent, then we're going to neglect to show that, and that's why you don't see any parentheses with an iteration number in this equation. So the total error is equal to the average of the two error components, each of which is calculated as the difference between the ideal output and the estimated or the calculated output squared. Now we can expand this expression as shown below. Again, we have two components, one for E5 and one for E6. So we have the 0.5 coefficient that comes from the expression above, and we calculate inside the parentheses the difference between the first element of the ideal output array for a given sample minus the estimated value, which is generated by applying the sigmoid activation function to the H superscript 5 weighted sum. So right, we have the weighted sum of the synapse weights, their activation values, 2 times because there's 2 synapse connections coming into node number 5, and then we repeat the same thing over here for node number 6, right? The second element of the output or ideal output array is associated with x6, and we subtract from that the calculated or the estimated output. We apply the sigmoid activation function to H superscript 6, which is the weighted sum of the synapse weights and activation values or states that are associated with it or connected directly to it. Now, unfortunately, differentiation with respect to the hidden layer synapse weights, W13, W23, W14, and W24, is going to be more difficult. Before moving on, I did want to discuss specifically why it's relatively easy or relatively straightforward to differentiate the two error components E5 and E6 with respect to these 4 synapse weights. Now, this expression may look messy, it may look complicated with its weighted sums, it has a lot of terms, it employs this sigmoid functional structure, but overall it's really not that bad, right? We have an expression for the total error that is defined explicitly in terms of the 4 synapse weights of interest, and so although it may not be fun, it's not that difficult to calculate the partial derivative of the total error with respect to one of these values. Let's say, for example, the synapse weight 3, 5. Now, unfortunately, differentiation with respect to the hidden layer synapse weights, W13, 23, 14, and 24, is more difficult. Why? Because we don't see those parameters up here, right? It's more difficult because these hidden synapse weights, or hidden layer synapse weights, have only an indirect effect on the mean squared error via the intermediate values x3 and x4. Furthermore, we don't have ideal labeled states for x3 and x4, so we can't simply repeat this process for the hidden layer, as we don't ideally know what outputs the hidden layer should generate. This figure will allow us to reinforce some of the statements from the previous slide. In the green, we have the 4 output layer synapse weights, and they have a direct effect on the mean squared error as generated by x5 and x6. In the purple, we have the 4 hidden layer synapse weights, and they have only an indirect effect on the mean squared error through the intermediate states x3 and x4. So we have ideal values for x5 and x6 because those correspond to the first and second ideal outputs, but we don't, again, have ideal values for this x3 and this x4. So now we jump into the supervised machine learning process, or more specifically of interest here, the backpropagation process is part of that. We begin with an untrained neural network that cannot yet classify handwritten digits as 0 or 1. Remember, the untrained neural network structure is not enough to achieve this task. We need to optimize our synapse weights. Initially, the synapse weights are pseudo-randomized as done by PyTorch. Training samples are then supplied to the supervised machine learning algorithm that in turn searches for the optimal synapse weights, which we call W or W sub OPT. Now, I did want to take a look at the figure to the right, this is training sample number 2, specifically the training sample we're going to use for iteration 0 and for our step-by-step look at backpropagation. Ideally, it's a 0, as you can see, and the sensors yield 2 different values. So there's very little ink here in the middle in the blue region, so we get a value of 3.1% coverage for X1, and there's a lot more ink out here in the exterior regions, and so we get a value of X2 that is 23.5%. So one way we can begin to understand backpropagation is to ask, what effect does a single training image, like the 0 up here, have on the synapse weights within a neural network as we update them from one iteration to the next as part of supervised machine learning? And we're going to answer this question by performing a single iteration of backpropagation as well as gradient descent, and we're going to do this manually, step by step, and again relying on stochastic gradient descent, a topic that we're going to come back to sooner or later. So one thing I would like to say up front is that backpropagation, or perhaps it's more appropriate to say a single iteration of supervised machine learning via backpropagation, can be divided into 2 stages. So we have our forward pass and we have our backward pass. The forward pass begins at the input, executes the hidden layer calculations, essentially calculating the weighted sum of the synapse weights and the activation values or states, as well as applying the rectified linear unit activation function, and then generates the outputs as dictated by the output layer neurons. Again, you need the weighted sum and to apply the sigmoid activation function. So each neuron generates its respective output. The forward pass generates the results used to calculate the estimated output, and it also calculates the mean squared error, or the loss associated with both the 5th and the 6th states, which we call y estimated 1 and 2. So after the forward pass is complete for a given iteration, we begin the backward pass, or what is more traditionally referred to as the actual backpropagation. So it begins at the outputs, right, using the mean squared error, calculates the gradients and updates for the output layer. So now we're moving to the left, and then repeats this for all of the hidden layers going back to the initial input. And chain rule is applied to define all the unknown partial derivatives. The goal is to update all the synapse weights and prepare for the next forward pass for the next iteration. And we employ gradient descent for this purpose. So let's provide a step-by-step description of a forward pass. The first step is to initialize our model or initialize our neural network. Now for this example, this was done pseudo-randomly. We have 8 synapse weights total. 4 of them, right, as shown here, were initialized to a value of 0.01. 2 are initialized to a value of 1. 1 is initialized to a 2, and another one is initialized to 3. You can read the values on your own. All of these, as shown by the parentheses superscript, are for iteration 0, right? This is our initialization. We're not going to consider bias values for this example, but it doesn't really affect the math because we could always reintroduce the biases as a synapse connection originating from a neuron with a constant value of -1. So the second step is to choose the training sample for the current iteration, for iteration 0. And again, I admit this is really only necessary for the single element stochastic gradient descent, a topic that we will come back to in 1 or 2 modules. We begin by using training sample number 2. We introduced this training sample a couple slides back. And so what we end up with are these input values. X for sample number 2, the first element, is equal to 0.031, and this comes directly from the training data. And then we have X for sample number 2, second element, equals 0.235, again, coming from our sensors, our spatial averaging method, and then stored within the training data matrix. So variable s tells us which training sample is the focus of this iteration. We can also use it as a function where s of 0 tells us what sample is associated with iteration 0. In this case, as we've said before, it's sample number 2. So we have our input states. We also have our ideal output, which in this case is a 0. Then we can move on to performing the forward pass or the forward propagation. And so we'll begin with our inputs and then calculate the various intermediate and final outputs moving from left to right. So let's take a quick break to discuss notation, because this is the notation I'll be using in this as well as several upcoming modules. This variable, this symbol, represents the synapse weight between neurons K and M for iteration IT. The bracketed subscript is the origination neuron K, the bracketed superscript is the destination neuron M, and the parentheses superscript is the iteration number. For this entire slide, we'll see that the blue brackets represent the element indices, the red parentheses represent the iteration indices, and the green curly brackets represent the sample indices. Now this notation carries forward, it's just that the colors are specific to this slide. Next, we move on to inputs. This symbol, this variable, represents the kth element of input array X associated with sample S. If you remember, when we looked at the training data set, what we saw was 10 rows, 10 training data samples, and each one has an array that contains 2 values. So the blue bracketed superscript tells us whether it's the first or the second input, and this tells us with which sample it's associated. Now we can use the variable s as a function, so s of it would then tell us what sample is associated with the given iteration, and we'll discuss this more in a few modules when we come back to batch and stochastic gradient descent. Here we have 2 examples of outputs, the ideal and the estimated. Both are indexed in a similar way, right, where M represents the element of the output array. Again, we have 2, the first or the second, as well as the sample associated with that output. And so the notation is the same for both the ideal and the estimated or the calculated value. And now we can finally begin our forward pass. We start off with the input values pulled from the training data set, as well as the initialized synapse weight values. We calculate our weighted sum, which we refer to as H superscript 3, and then we apply to it the rectified linear unit activation function, which yields a value of 0.235, again this is for iteration 0, 0.235 for x3 and 0.033 for x4. These values will be fed down to the output layer, where we calculate x5 as the weighted sum again, and this weighted sum would be h5. So we have our weighted sum, we apply to it the sigmoid activation function. This yields a value of 0.517 for x superscript 5. That's also the same as the first estimated output. We do the same thing for x6, and we end up with a value of 0.670, and that's the same as the second estimated output. Again, remember, we're not going to use the iteration or the sample superscripts when all of the values in a given calculation are for the same sample and are for the same iteration. So we can look at these calculations from the previous slide in the context of the network as shown here. So this equation calculates x3, this equation calculates x4. These values feed into the output layer as dictated by these synapse connections here. We calculate x5, which is the same as the first estimated output, and we calculate x6, which is the same as the second estimated output. To visualize backpropagation, we begin by reviewing the ideal and estimated or calculated neural network outputs. So here we see the first element of the output array. We have the estimated or the calculated value associated with iteration 0. And the neural network, following the forward pass, generated a value of 0.517, and we just demonstrated how to calculate that. The ideal value is 1, because the handwritten value, as we saw, is a 0. The label equals 0. Then for the second output, right, the second estimated or calculated output for iteration 0 yields a value of 0.5083, and the ideal second element value is equal to 0 because the label is not equal to a 1. This is a 1 because the label is equal to 0. This is a 0 because the label is not equal to 1. We observe that to minimize the loss or the error, backpropagation and gradient descent must adjust the network synapse weights such that the first estimated output increases, bringing 0.517 closer to 1, and the second estimated or calculated output must decrease, bringing 0.5083 down closer to 0. Below, we label the network states for iteration 0 as associated with sample number 2, and all of these values were generated by the forward pass that we just completed. We started off with the inputs taken directly from the training data set, the second row of the training data set. We then applied the forward pass to the hidden layer, which gave us the values of x3 and x4, 0.235 and 0.033. We then applied the forward pass to the output layer, which gave us the value of x5 as 0.517 and x6 as 0.670. We've already seen previously that y superscript 1 is equal, or y estimated superscript 1 is equal to x5. The second element is equal to x6. So this value here is the same as this value here. This value is the same as this value. And we can compare it to the ideal outputs. Now, the other thing that we did to this figure is we increased or decreased the thickness of the synapse connections to represent their relative effect on the output. Now, this wasn't done in terms of the synapse weight value. It was done in terms of the activation value, or the state from which it originates. Connections that originate from neurons with larger outputs, larger activation values, larger states will have a greater effect on the overall output, right? Because these synapse weights would be multiplied by larger values as part of the weighted sum. Recall, we previously concluded that ideally, the first estimated or calculated output, which is equal to x5, should increase, and the second estimated or calculated output that's equal to x6 should decrease. So we know how the outputs should change, but I want to ask how the output layer synapse weights should change. If we take these two statements to be true, we know that the weights contributing to those outputs should experience a similar change. W35 and W45, right, the two synapse weights that feed in to x5 should increase, such that x5 increases, and W36 and W46, the two synapse weights that feed into x6, should decrease. Now this only works with the assumption that all the activation values, all of these states, are positive, they're greater or equal to 0. Knowing that, it's relatively straightforward to visualize these relationships for the output layer synapse weights, right? We see that W35 should increase, that's why it's shown in green. We see that synapse weight W45 should increase, it's shown in green, and then we can see the others shown in red. But what about for the hidden layer? We're going to see that this is more difficult. One quick note here, I did remove some of the coloring from other parts of the figure from the last slide to this one, so we can focus on the green and red denoting whether values should be increasing or decreasing. So next I ask a slightly more difficult question. How should the hidden layer synapse weights change? Let's think for a second. Suppose we remove the output layer synapse connections that have a minimal effect on the output for iteration 0. Essentially, we remove this one here and this one here, because for iteration 0, the synapse weight 3,5 has a pretty small value. It's pretty close to 0. Same thing for the synapse weight between neurons 4 and 6. So those are grayed out. We no longer are going to take those into account. With those gone, it simplifies the network structure, and we can then observe that the first estimated or calculated output that's equal to x5 really depends more strongly on x3, as shown by this connection here. And the second estimated or calculated output equal to x6 depends more strongly on x4, as shown by this connection here. And from those relationships described on the previous slide, we can make a similar conclusion as what we use for the output layer. x3, like x6, should decrease. x4, like x5, should increase. And this is because on that previous slide, we demonstrated a strong correlation between those two values. If we take this to be true, we can also conclude that the synapse weights that feed into x3, just like the ones that fed into x6, that's W13 and W23, they should decrease. The synapse weights that feed into x4, just like the ones that fed into x5, right, they should increase. And so we add those conclusions to the ones we made previously, yielding the figure below. And so this gives us a good idea in the green of what synapse weight values should be increasing as we go from iteration 0 to iteration 1, and in red we see the synapse weight connections that we expect to decrease as dictated by the combination of backpropagation and gradient descent. Now, to provide a slight spoiler, I've shown over here the results of the simulation we're going to run for the next module, and the conclusions of our visualization over here match the formal calculations or match the results generated by our simulation. Over here we can see W13, the value decreases when we go from iteration 0 to 1. W23 also decreases. W14 increases. So what we can see is all the red values match the red synapse weights over here. The green values match the green synapse weights over to the left. Now, our visualization provides the direction in which the synapse weights should change, but we will require some more formal math in order to determine what the magnitude of those changes should be. The visualization that we just presented show that updating the output layer synapse weights is relatively straightforward. For the hidden layer, however, the backpropagation algorithm must determine how each hidden layer activation value or state influences the layers that follow it. While there are no explicitly ideal hidden values, there's no ideal value for x3 that we can take from the training data set, we can estimate the direction and the magnitude of the change needed, or the ideal change associated with x3. This estimation depends on the synapse weight values and the activation or the state values in subsequent layers. Now let's not forget that each update is also proportional to its associated error. So we were really focusing on the effect of the magnitude of the states or the activation values on how much the synapse weight change, but they're also dependent on the synapse weight values themselves as well as the magnitude of the associated error. The backpropagation algorithm formalizes this process and allows us to compute more precise gradients between any output, essentially any of the errors or the losses, and any synapse weight. Note that this visualization would change slightly if negative states or negative activation values were considered. In conclusion, this module introduced the concept of backpropagation, demonstrated how to set up the necessary calculations, and provided an overview visualization of the process. Watch the next module to see a mathematical formulation of the backpropagation process, as well as the results of an Excel-based simulation that we applied to the 0-1 handwriting recognition example.